Hello friends, in this module we shall discuss Kirchhoff's law and analysis of multiple loops circuits. Objectives: first, to understand the concept of Kirchhoff's current law. Second, to understand the concept of Kirchhoff's voltage law. Third, to understand sign conventions for solving complicated circuits. Fourth, to analyze multiple loop circuits. Ohm's law can be useful for determination of the value of resistance of the resistor or current in simple electrical circuits. But most of the electrical circuit consist of number of resistors and sources interconnected in complicated manner, and such electrical circuits are named as network circuits. For the determination of the distribution of currents in a complicated network circuit, we can try to reduce the complicated network circuit to some simple series parallel combinations. Gustav Robert Kirchhoff first developed a method to solve such a complicated network circuits, which follows from Ohm's law and conservation of charge and energy. Kirchhoff proposed two laws. First, Kirchhoff's current law, that is KCL. Second, Kirchhoff's voltage law, that is KVL. First, Kirchhoff's current law. Kirchhoff's current law states that the algebraic sum of the currents at any junction, that is node, is 0. Kirchhoff's current law follows from the principle of conservation of charge, that is equation of continuity, and the fact that there can be no accumulation of charge at any point in the circuit. It can be written as summation of I is equal to 0. This law is also called Kirchhoff's point rule, Kirchhoff's junction rule or nodal rule, and Kirchhoff's first rule. Following sign conventions are used to find the algebraic sum of currents. The current flowing towards the junction is treated as positive. The current leaving the junction is treated as negative. In above figure, currents I2, I4 and I5, which are flowing towards the junction O, are positive, and currents I1 and I3, which are leaving the junction O, are negative. Therefore, according to Kirchhoff's current law, minus I1 plus I2 minus I3 plus I4 plus I5 is equal to 0. That is, summation of I is equal to 0. This law follows from the principle of conservation of charge. Current being the rate of flow of charge, currents I2 plus I4 plus I5 represents the total charge flowing towards the junction O per second, while currents I1 and I3 represents the total charge leaving the junction O per second. As there is no accumulation of charge at the junction, it can be written as I2 plus I4 plus I5 is equal to I1 plus I3. That is, minus I1 plus I2 minus I3 plus I4 plus I5 is equal to 0, or summation of I is equal to 0. Second, Kirchhoff's voltage law, that is KVL. The algebraic sum of the EMFs taken along any closed network current loop is equal to the algebraic sum of the product of the current and the resistance of each link of the current loop. That is, summation of E is equal to summation of IR. This law, also called Kirchhoff's second law, Kirchhoff's loop or mesh, and Kirchhoff's second rule. Kirchhoff's voltage law is based on the law of conservation of energy, that is, energy given or taken by potential field, not including energy taken by dissipation. Due to a given voltage, a charge which is completed a closed loop does not gain or lose energy as it has gone back to its initial potential level. Even when the resistance which causes dissipation of energy is present in a circuit, KVL holds true. In this case, a charge in fact does not go back to its starting point due to dissipation of energy. A charge will just terminate at the negative terminal instead of positive terminal. This means all the energy given by the potential difference has been fully consumed by resistance, which in turn lost the energy as heat dissipation. In short, Kirchhoff's voltage law has nothing to do with gain or loss of energy by electronic components like resistors, capacitors, etc. It is a law referring to the potential field generated by the voltage source. In this potential field, in spite of what electronic components are present, the gain or loss in energy given by the potential field must be 0 when a charge completes a closed loop. The product IR represents the potential difference, that is PD, across the resistance. By definition, it is equal to the energy required to send a unit charge through the resistance. Thus, summation of IR gives the total energy required for the flow of unit charge around the closed circuit. The EMF, that is E, of cell is equal to the energy supplied by the cell to send a unit charge around the circuit. Thus, summation of IR is the total energy per unit charge supplied to the circuit, while E is the total energy used in the circuit. According to law of conservation of energy, energy supplied is equal to the energy used in the circuit per unit charge. That is, summation of E is equal to summation of IR. This is equation 1. Note, E does not have dimensions of energy. Its dimension is energy per charge. A closed current loop is a path such that starting from any point of the circuit, one returns to the same point after travelling along all the resistance and sources of electricity in that path. It is not necessary to consider any other components branching out from any point of the current loop. The current loop may be traced in any sense, clockwise or anticlockwise. A rise in potential should be considered as positive and a fall in potential should be considered as negative. While applying equation summation of E is equal to summation of IR, the following sign conventions are used. While going from negative terminal of the source to the positive terminal, there is a rise in potential. Hence, in such a case, the EMF should be considered as positive. While going from positive terminal of the source to the negative terminal, there is a fall in potential. Hence, the EMF should be considered as negative. In case of resistor, if we go through it in a direction of current, there is a fall in potential because the current always flow from the point at higher potential to the point at lower potential. So, potential drop across resistor in such a case should be considered negative. In the case of resistor, if we go through it in the opposite direction of a current, there is rise in potential because the current always flow from the point at higher potential to a point at lower potential. So, potential drop across resistor in such a case should be considered as positive. To understand sign convention, consider the closed loop shown in the following figure. Assume that the loop PQRSP is transversed in clockwise sense. By applying Kirchhoff's voltage law to the loop PQRSP, we get minus V1 plus I1 R1 plus V2 minus I2 R2 minus I3 R3 minus I4 R4 is equal to 0. First, V1 is negative because a source of EMF is traversed from its positive terminal to negative terminal, that is fall of potential. Second, I1 R1 is positive because we are going through resistor R1 in the opposite direction of current flowing through it, that is rise in potential. E2 is positive because a source of EMF is traversing from its negative terminal to positive terminal, that is rise in potential. I2 R2 is negative because we are going through resistor R2 in the direction of current flowing through it, that is fall in potential. Fifth, similarly I3 R3 and I4 R4 are taken negative because there is a fall in potential in each case. To understand the sign conventions, consider another closed electrical circuit containing 3 closed loops as shown in following figure. It consists of 3 closed loops. First, PQRSP, second SRTVS, and third PQTVP. The current distribution is shown in the figure. Assume that each loop to be traversed in the clockwise sense and applying Kirchhoff's second law to each loop. We get 3 equations. For the loop PQRSP, minus V is equal to minus I1 R2 minus in bracket I1 minus I2 bracket complete R6 minus I1 R1. Here V is negative because a source of EMF is traversed from its positive terminal to negative terminal, that is fall of potential. I1 R2 is negative because we are going through resistor R2 in the direction of current flowing through it, that is the fall of potential. I1 minus I2 R6 is negative because we are going through a resistor R6 in the direction of current flowing through it, that is fall of potential. I1 R1 is negative because we are going through resistor R1 in the direction of current flowing through it, that is fall of potential. For the loop SRTVS, in bracket I1 minus I2 R6 minus I2 R3 minus I2 R4 minus I2 R5 is equal to 0. For the loop SRTVS, source V is 0. Here I1 minus I2 R6 is positive because we are going through resistor R6 in the opposite direction of current flowing through it, that is rise in potential. I2 R3 is negative because we are going through resistor R3 in the direction of current flowing through it, that is fall of potential. I2 R4 is negative because we are going through resistor R4 in the direction of current flowing through it, that is fall of potential. I2 R5 is negative because we are going through resistor R5 in the direction of current flowing through it, that is fall of potential. For the loop PQTVP, minus I1 R2 minus I2 R3 minus I2 R4 minus I2 R5 minus I1 R1 is equal to minus V. In this loop, here V is negative because a source of EMF is traversing from its positive terminal to negative terminal, that is fall of potential. I1 R2 is negative because we are going through resistor R2 in the direction of current flowing through it, that is fall of potential. I2 R4 is negative because we are going through resistor R4 in the direction of current flowing through it, that is fall of potential. I2 R5 is negative because we are going through resistor R5 in the direction of current flowing through it, that is fall of potential. I1 R1 is negative because we are going through resistor R1 in the direction of current flowing through it, that is fall of potential. Using these three equations, the unknown current and resistance can be determined. Resistor in series circuit. Analysis of series network current. Step 1. Find the equivalent resistance of the circuit. The equivalent resistance equal to the sum of all series resistance. Step 2. When resistors are in series, apply KVL directly. The sum of the individual voltage drop, that is V is equal to IR, equals the applied voltage. Let us calculate the current in series network circuit. Consider a circuit containing battery of 18 volt connected across series combination of 3 resistors R1, R2 and R3. Step 1. Find equivalent resistance of the resistor in series network circuit. Equivalent resistance R equivalent is equal to R1 plus R2 plus R3. Therefore, R equivalent is equal to 2 kilo ohm plus 3 kilo ohm plus 4 kilo ohm, that is R equivalent is equal to 9 kilo ohm. To find voltage drop across each resistors, we first find the current flowing through the circuit. We know V is equal to IR. Therefore, we can write I is equal to V upon R equivalent. By putting the values of voltage and R equivalent, we can write I is equal to 18 upon 9 into 10 raised to 3. Therefore, we get I is equal to 2 into 10 raised to minus 3 ampere, or I is equal to 2 milliampere. Step 2. Find various voltage drop across each resistors. V1 is equal to I R1. V1 is equal to 2 into 10 raised to minus 3 into 2 into 10 raised to 3. V1 is equal to 4 volt. V2 is equal to I R2. V2 is equal to 2 into 10 raised to minus 3 into 3 into 10 raised to 3. We get V2 is equal to 6 volt. Similarly, V3 is equal to I R3. V3 is equal to 2 into 10 raised to minus 3 into 4 into 10 raised to 3. We get V3 is equal to 8 volt. Sum of voltage drop across resistors is equal to total voltage applied. So, we can write 4 volt plus 6 volt plus 8 volt is equal to 18 volt. Open in series circuit. In a series circuit, if the circuit is opened anywhere, it offers infinite resistance. Hence, zero current will flow through the circuit and there would be no voltage drop across series resistors. While whole voltage drop would be developed across the open end of the circuit. Short in series circuit. In a series circuit, if there is no resistance, that is zero resistance, and if EMF is present, the circuit is said to be shorted. In such a case, an infinite current should flow. According to Ohm's law, I is equal to V upon R. Here, R is equal to 0. Therefore, I is equal to infinite. But in practice, resistance is never completely absent and also not remain constant for real voltage source. So, there are no infinite currents. Resistor in parallel circuits. A branch arrangement of components connected in circuit across voltage source form a parallel circuit. Resistor in parallel circuit, voltage across each branch is same, therefore apply directly KCL, that is Kirchhoff's current law. Analysis of parallel network circuit. Step 1. Find equivalent resistance of the resistor in parallel network circuit, that is 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus dash 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 plus 1 upon Rn. Step 2. When resistors are in parallel, apply Kirchhoff's current law directly. In each branch, there are divisions of currents. The sum of branch currents is equal to total current supplied by a source. Let us calculate current in a parallel circuit. Step 1. Find equivalent resistance of the resistor in parallel network circuit. Here R1 is equal to 2000 ohm and R2 is equal to 3000 ohm. Therefore, 1 upon R equivalent is equal to 1 upon 2000 plus 1 upon 3000. We get 1 upon R equivalent is equal to 5000 upon 6000. R equivalent is equal to 6000 upon 5000 ohm. Let I be the current distributed by the 12 volt battery. V is equal to IR equivalent. Therefore, I is equal